Next concept is EM waves. So far, we have discussed about alternating current. Now let's discuss about EM waves. What is EM waves? It is electromagnetic waves. Why are they called as electromagnetic? Because these waves, they consist of both time varying and position varying electric field as well as magnetic field. And they oscillate in such a way that they transfer energy from one location to another location. Okay. Now, what are the important topics we are going to discuss in EM waves? First one is we are going to just write about the four Maxwell's equations. Second one, we are going to discuss about displacement current. And third, we are going to discuss about transverse nature of EM wave. Transverse nature of EM wave. And then Poynting vector. And the last concept is about energy density of an EM wave. Okay. Starting with Maxwell's equations. So Maxwell, he gave us four equations to understand entire electromagnetic concepts or entire concept of electromagnetism or about electromagnetic waves. What are those four and fundamental equations? Maxwell's fundamental equations. The first one is closed integral of E bar dot ds pi. Basically, it's the Gauss law. Is charge enclosed by epsilon naught. Second one is integral b bar dot ds bar is 0 because in case of magnetism, we can never find a unipole. If there is a north pole, there is obviously a south. So for a magnet, the net flux coming out of any surface is always 0, right? Because there are no unipoles, there are always bipoles. Next one is Ampere's circular law, that is d bar dot dl bar is mu naught into I enclosed. And the last one is integral E bar dot dl bar is 0. This is Ampere's law for electrostatics. That is, the work done by electric field in a closed loop is always 0 because electric field is a conservative. Electric field is a conservative field over here. So these are the four fundamental equations of given by Maxwell, which can explain the entire electromagnetic field. We don't have to dig into what are these equations are because we know what is this, this, and this. This is something which we have learned, but it is understood, right? That is closed integral of E bar dot dl bar is 0. We just have to remember these four equations because we can just get a direct question asking which of the following is Maxwell's equations, right? That's the first one. Now, the next concept is about displacement current. What is this displacement current? To understand this, we'll first do an experiment. That is, let's take a capacitor connected to a switch, then a battery. And then we'll take two galvanometers. One is right next to this wire, and one is between the plates of this capacitor. Okay. As soon as you close the switch, you can see that there is a deflection in this galvanometer because there is flow of current, and any flow of current will create a magnetic field over here. This magnetic field will influence the needle of the galvanometer or needle sorry, this magnetic field will influence the magnetic needle, which will show some deflection. Similarly, over here also you can see that there is some sort of deflection in this magnetic needle. But why? Why are we able to see this deflection between the plates? That implies I can say that as soon as you close the switch, until the plates get charged from 0 to plus Q and this one from 0 to minus Q, there is charge buildup. That means the charge is continuously increasing. As the charge is continuously increasing, there is a variable electric field that is created over here, or a time varying electric field is created. And this time varying electric field can always create a magnetic field, just like a time varying magnetic field can create an electric field, which we have learned in electromagnetic induction. But this particular current is never explained, right? So we have a corrected equation or corrected Ampere circuit law corrected by Maxwell, and that is integral of B bar dot ds bar is mu naught times of the conduction current is the current which is actually flowing through the wire, that becomes the conduction current, and the current which is flowing, which need not actually have a physical appearance, but it is assumed to flow between the plates of the capacitor when it is being charged, we call it as displacement current ID. And this value of displacement current ID is given by epsilon naught into d phi by dt. And this flux is rate of change. This flux is electric flux. Remember, it's not magnetic flux, rather it is electric flux. That's why it is called as Maxwell Ampere circuit law, which is corrected by Maxwell. Because Maxwell is the one who has introduced this displacement current. Which is given by epsilon naught into d phi e by dt, right? The next one is transverse nature of EM wave. What is this transverse nature of EM wave? So here we learned that this electromagnetic wave has both electric field as well as magnetic field. But how do they oscillate? They oscillate perpendicularly, somewhat like this. If electric field is oscillating in one plane like this, the magnetic field will be oscillating in a plane which is perpendicular to this electric field like this. Let's say this is Z and this is Y, and the propagation is along X. So Y is where electric field is oscillating, whereas along Z we have magnetic field oscillating. Now observe carefully these two. I can say that the frequency of electric field and the frequency of magnetic field is zero. Because when electric field is zero, even the magnetic field is zero. When electric field is maximum, even the magnetic field becomes maximum or one of its extreme. And again, when electric field becomes zero, even the magnetic field becomes zero. So we can say that the lambda frequency time period, whatever it is same for both electric field as well as magnetic field. Right? Only the difference will be the amplitude. Amplitude of electric field will call it as E naught, whereas amplitude of magnetic field will call it as V naught. Right? But what about the direction? How do we know its direction? Before that, let's write down a simple equation or the wave equation for electric field. Let's say electric field is oscillating along y-axis, but the propagation is along x-axis. So E bar is given by E naught into sine of omega t minus kx, whereas B bar is given by V naught into sine of omega t minus kx. Here, B bar is oscillating along z-axis, so we will write it as k cap. Now, the direction of propagation of the wave is always along the direction of E cross B divided by mu naught. We call this as a Poynting vector S bar. Poynting vector basically gives us the direction of propagation of the wave or the direction of propagation of the energy. Where here S bar is called as what? Poynting vector. Right? Now, the speed of this electromagnetic wave C is given by 1 by mu into epsilon, where mu and epsilon are the permeability and permittivity of that particular medium. Now let's see speed of light in vacuum. Let's call it as V. That would be easy. Speed of light in vacuum is given by 1 by mu naught into epsilon naught, because mu naught and epsilon naught are the permeability and permittivity of free space. When you substitute the values, you will get it as 3 into 10 power 8 meter per second. Because C is dependent on permeability and permittivity, because C is nothing but speed of electromagnetic wave. And this electromagnetic wave is definitely influenced by the electric and magnetic properties of that particular medium, which are determined by permeability and permittivity of that medium. Isn't it? The next concept that we have is energy density. So obviously, since we have electric field and magnetic field, obviously they carry some energy. We are going to discuss about the energy density of this. So energy density associated with electric field is half epsilon naught E square. This we have learned earlier. Let's call it as U. Energy density associated with magnetic field is given by B square by 2 times of mu naught. So the total energy density is energy density due to electric field plus energy density due to magnetic field, which is half epsilon naught E square plus B square by 2 mu naught. But these are the direct electric field and magnetic field. But if I take the average of this energy density, U average, it becomes 1 by 4 epsilon naught amplitude of E square plus amplitude of B square by 4 mu naught. And always remember, the energy is equally divided across the electric field and magnetic field. So this can also be written as half times of epsilon naught E naught square, which can also be written as B naught square by 2 times of 2 mu naught, because the energy is equally divided across electric field and magnetic field. We cannot say that an electromagnetic wave is having more energy associated with electric field and less energy associated with magnetic field. These are the important concepts related to electric field, because beyond this, there will not be any questions asked from this apart from electromagnetic spectrum. That is something which you can read, right?